Electromagnetism, lesson 4, the motor effect. Now, what we're just going to do before we actually move on is we will just revise a little bit of the work that we've done previously to this. So, what we've got then is quite simply, if we take a magnet with north and south, we sprinkle iron filings on around it. What we can see is we can see a magnetic field around it. If we take a set of plotting compasses, we can actually find out more detail about the magnetic field around it. First of all, it's shaped in this sort of concentric, sort of oval shaped, and it's got a direction, the magnetic field that moves from north to south. Now, what you can also see as well is we represent this magnetic field with these field lines here. The more of them in a particular area means the more dense the magnetic field is. So more field lines equals more dense magnetic field, which equals a stronger field. Now, what we've got then is this idea of a magnetic field around a magnet. Now, if we run a coil of wire and we run a current through it, what will happen is the current moving through it will set up a magnetic field around it, and that magnetic field will be shaped for a coil of wire like our bar magnet, and it will have a direction of north to south. Now, we'll talk a little bit more about these later. These are solenoids, okay? Now, the reason for this is because magnetic fields are caused by moving particles, in particular moving electrons. So when these move, we have a magnetic field. Now, this was first established by Ørsted, who conducted a little experiment to try to show that there wasn't a link between electricity and magnetism. And much to the delight of the students that were watching, he found that there was a connection between electricity and magnetism. Now, this work was then taken on by James Maxwell Clark, who took it a step further. And he did some work based around the direction of the magnetic field around a wire that carried a current. So there we go. There's our wire. Let's just connect it up. Let's say positive down here. Sorry, down here, and negative here. What this means then, if we connect this up, we will have current flowing upwards. Now, if we were to do this on a bit of card, we would see, we would start to see a magnetic field being established around the wire. So if we sprinkle some iron filings around this, what we would see concentric rings being formed. Now, you can repeat this and have the current flow in the opposite direction. And again, if you sprinkled iron filings around it, you would see that they would form concentric circles, like so. and these would be at 90 degrees to the wire, perpendicular, if you like. Now, what Maxwell Clerk did was he put some little plotting compasses around the wire. And what we found, or what he found, was that the magnetic field around the wire deflected the magnet in a direction. In fact, when the current was moving upwards, in this case, positive to negative, he found that the compasses, the compass needles, were deflected and showed that the magnetic field was actually in a anti-clockwise direction. We reverse the current, so it's going downwards here. You could see as it was going in a clockwise direction. Now, this is quite handy to remember that you can actually determine the direction of this field using the right-hand grip rule. So, if this is our wire, and in this case the current's going positive, negative, so it's going upwards, you can take your right hand and you can grip it. You have your thumb going in the direction of the wire that the current is going in, upwards in this case, like so. Now you can see that your fingers, the direction of your fingers will tell you the direction of the magnetic field. In this case, it's anti-clockwise. Now if we reverse this, it goes down, and what you can see is there's an arrow there, you can see that the magnetic field goes clockwise, it follows my fingers there. So this is the right-hand grip rule, which is useful finding out the direction of the magnetic field around the wire. Oh. Now what we're going to do then is just take us back to PowerPoint. Now, you'll see on the PowerPoint that you've got those 3 questions. You should be able to answer number 2 now if you're using the right-hand grip rule. Now, what we're going to do in this lesson is look to see how to change the size and direction of the force in a current carrying conductor in a magnetic field, what we mean by magnetic flux density, which I've just clicked on there, and how to calculate the force in a current carrying wire. So now, I mentioned earlier about Ørsted. This is a link to Ørsted's little experiment. As you can see, you've got your compass there, and you can see its deflection. So, and we have our current carrying conductor here, compass deflected, compass needle deflected. Now, if you click on that link, it'll take you to that little YouTube video, which might explain it in a little bit more detail with some nice diagrams. Now, here we're moving on to the motor effect. So, what we've actually got then is this is our current carrying conductor. Our current carrying conductor moving through will have a magnetic field around it that's at 90 degrees to it. Now that magnetic field, okay, will interact with the magnetic field of the magnet. And if you've got 2 north poles, you get repulsion. If you've got north and south, you get attraction. So if we have a magnetic field around the wire, what this means is that that magnetic field will interact with the magnetic field of our magnet, and it will cause movement, attraction or repulsion. If we press this switch here, there you go, you can see that we've got movement. So we can actually determine that movement by the direction of the current, the direction of the magnetic field. To do this, what we do is we use Fleming's left-hand rule. So what you'll need to do is you'll need to take your left hand, hold it up, and you'll put your thumb, first finger and second finger at 90 degrees to each other. Now, your thumb is all about motion. First finger is about field, and your middle finger is about current. What you've got to do is you've got to look at this, and I remember it as being Manchester Football Club. So we go with Manchester Football Club, motion, field, current. You can see on here that we've got pretty much the same Manchester Football Club. However, it's a different way of remembering it. Thumb, M for motion. First finger for field. Second finger, current. If you want to remember it like that, that's fine. Now, what we can do is we can use Fleming's left-hand rule to determine the direction the wire moves in. Here, we can see what determines the size of the movement. If, let's say, we include a bigger battery or more, which bigger potential difference, which cause more current to flow, then you will have more of a force. If we change the strength of the magnetic field here, once again, we will have a bigger force. If we change the length of wire that's in there, the number of coils, let's say, that are in there, again, you will change the amount of force acting on the wire. Now, what we've got here are a couple of YouTube links. We've got the free science lessons. So if you click on that, that'll take you there. And then we've also got a video that I've produced showing why we get this movement, looking at what happens between the interaction between our magnetic fields here. Okay. So we work through this, and we can get to this idea of magnetic flux density. So the magnetic flux density is determined by the magnetic field. Strength of the magnetic field. Here we go. The strength of the magnetic field. There we go. We'll go north, and south. So if there are more magnetic field lines in there, we will have a stronger magnetic field, and we will have more of a force acting on a wire that's in that magnetic field. What we can also say is that this is my magnet here. I'll draw this 2 dimensions. There we go. There we go. There's north and there's south. Now, the actual length of wire in that magnetic field of the wire in the magnetic field will also determine the force. If we take the force, it's determined by the strength of this magnetic field, and it's also proportional to the length of the wire in the magnetic field, and also the amount of current flowing through there. So can see then is that the force acting on the wire causing that movement, okay, is determined by the magnetic flux density, B, in Tesla, times the current in amps, times the length in meters. Now, okay, this can now be written out as, and the one you want, you share, is this here. So you need to write out, make a note of force, write it out as a word equation first, equals magnetic field strength B in Tesla times current in amps times length in meters. You need to write that out then underneath as force is equal to B, which is our magnetic field strength in Teslas, times current, which is I, in amps, times length. So as you can see, force is equal to Bill. You need to make a note of this. Now, what this means is we can actually use this equation to calculate the force acting on the wire, how much movement we get, if you like. Or if we know the other three variables, such as force, current, and length, we can actually work out the strength of the magnet, its magnetic flux density between the poles. Or let's say, if we know force, magnetic flux density, and length, we can work out the current flowing through the wire. Or we could work out the length of the wire in the magnetic field if we know the other three variables. So this is a worked example. And there are some more worked examples here. Now in this PowerPoint, what I've done is I've clicked on a link. So if you can get your pink booklets out and work through those questions using that equation, force equals Bill, IL, and that would be great. And these are all the solutions. So quickly just move it on. So once you've done them, you can check your answers. What I'd also like you to do is, if you go to this booklet, you've got magnetism, electromagnetism, then on page 21 of your booklet, there are some questions. And I will put up links for those solutions to these questions in the email that's with this PowerPoint. Finally, you will need to look at, you have to bear with me because this is the first times I've done Zoom. So you've also got some a nice little closed passage there, which I'll attach. And finally, so I've attached this so you can cut this out and put this in your book along with your other notes. Now, hopefully that's made sense. And I'll stop here.